All right, well, it's 10. I suggest we get started. So welcome everyone at this fourth session of the Science at Low Frequencies number 7 meeting, which at one time, that seems ages ago and yet not, we hoped would be a live meeting. But it isn't. And on the other hand, of course, we now have a total of 370 or so participants, which is much more than we would ever get live. So your talk will likely be heard by more people than it otherwise would have been, but the interaction will be a little less personal. So once again, welcome everyone from every continent, whatever time zone it is right now where you are. And with that said, I propose that we go on to part 2 of our 3-part story on the epoch of reionization and cosmic dawn. And I would like to invite Anne Hutter from the University of Groningen to talk to us about tracing the topology with the 21 centimeter bispectrum during the EOR.
All right. Thank you very much. I hope you can see everything fine right now. So thank you very much. Thank you very much to the organizers to give me the opportunity to talk to you about the ionization topology and how we can trace it with the 21 centimeter bispectrum during the epoch of reionization. So I believe I don't need to give like a long introduction into the epoch of reionization. I think probably in the last session it was already clarified that the epoch of reionization describes the phase transition of the universe from a neutral to an ionized state, and this was mostly triggered by the first stars and galaxies. What I want to focus on is like one of the main questions I'm really interested in is like what are the sources of reionization, and particularly when we're talking about star-forming galaxies, what is the escape fraction of ionizing photons into the IGM? So this is basically within the galaxies, stars produce a certain number of ionizing photons, but only a fraction of those can escape into the intergalactic medium and start ionizing the neutral hydrogen there. And as you can imagine, if this escape fraction varies across different galaxies, then this will very closely link to actually your ionization topology. So how large are the ionized regions around these galaxies will be also crucially determined by what is your escape fraction. So by ionization topology, I mean the evolution of the sizes and the location of the ionized regions. So do we have a lot of large ionized regions, a lot of small ones? How do they evolve over time, and so on? So with the escape fraction of ionizing photons, there have been like a bunch of radiation hydrodynamical simulation. What they have been showing that the escape fraction actually depends very sensitively on the physical processes and particularly the gas distribution within the galaxies. So for instance, supernova feedback plays a huge role because it can basically blow out gas from low mass galaxies and provide low density tunnels through which the ionizing photons can escape from the ice and into the intergalactic medium. And so based with this motivation, what we have done, we have taken a semi-analytic galaxy evolution model, and we basically have implemented like 3 different models where I just want to present to you the resulting ionization topologies, like how different they can be. So what we have done is like we have the fiducial case where you basically can see, which is the middle panel, where we assume the escape fraction of ionizing photons is constant for all galaxies over all times. So then you can see like, so in each panel, so what is black is basically a neutral IGM, and what is sort of orange-yellow are the ionized regions. And we go basically from a nearly neutral universe to a more nearly ionized universe from the top to the bottom. So this is the fiducial model. And so what we have done then, we have looked at the other 2 extreme cases that the escape fraction scales with the star formation rate. So that basically corresponds to that increases with the halo mass. So this is what you see on the right-hand side. So what this results in that the most massive galaxies have also like even larger ionized regions, while the very low massive, least massive galaxies hardly have any small ionized regions around them. And if you go then to the opposite case, so the escape fraction basically increases with the ejected gas fraction. So this is a bit from the supernova ejection model inspired. We find that the escape fraction basically decreases with the halo mass. So what you find here then is that you have not as huge ionized region as in the other extreme scenario. Those ionized regions around the most massive galaxies are smaller, but on average, the ionized regions around the less massive galaxies are larger than in the other extreme scenario. So what we can say, if we look at all these panels, if we go from right to left, basically our ionized bubbles have a more and more similar size. So they, in a way, your ionizing emissivity becomes, if you want to put it like this, more homogeneous. And you can also quantify this by plotting the size distribution of the ionized regions. So this is what you see here in the left-hand panel. So at the bottom, you basically have the size. The color shows you sort of the probability density distribution or the size distribution. And along the y-axis, it's the mean neutral fraction of the universe. So on the top, the universe is basically nearly neutral, and at the top, it's basically ionized. And we can see when we look here at the peak of the size distribution, which is indicated by the solid line for the scenario where the escape fraction is basically decreases with halo mass, we can see that as the universe becomes more ionized, so the ionized bubbles grow, also the size distribution and the peak increases in size. And again, so what we discussed also earlier, we can see that these different topologies, what we already see from these ionization maps, you will have larger ionized region if your escape fraction increases with halo mass. And similar is actually true when you look at the neutral regions. So you find exactly the same behavior. Of course, like in the beginning, the neutral regions are the largest and their size decreases as the universe becomes more ionized. But however, you will also find that the case where basically here, the left-hand panel, they will have their peak of the size distribution at smaller sizes. So you will find here smaller neutral regions than here in the left-hand side. So I think this is also understandable if you consider that here you have far more small mass galaxies having detectable small ionized regions, which basically cut through what you otherwise would be considering as one neutral region. All right, so this is just to give you an overview what you would expect from these three different simulations, because I will use those to understand like the 21 centimeter bispectrum. So because the 21 centimeter signal from reionization is definitely non-Gaussian, the idea is like, if you look at the 21 centimeter bispectrum, which features in there can trace the ionization topology. So the question is here, so let me remind you. So the bispectrum is a Fourier transform of the 3-point correlation function. And you can see here the definition of the bispectrum. And you see here you have basically the product of the Fourier transform of the fields for 3 different k vectors. However, you can see that only those combinations will contribute to the bispectrum, which basically form a closed triangle in k space. And so you can see then here down here different triangle configurations. And the question is like, if you have a triangle configuration, what does that mean? To what kind of structure does that correspond in real space? Because drawing these in Fourier space might be very abstract and you have actually no idea what that corresponds to in real space. So, and here's a really nice plot from Catherine Watkinson, where she actually shows this very nicely. So each k vector you can imagine as a plane wave. as you can see here in the first 3 layers, and you form the interference between these 3 K vectors, and the resulting structure is basically what you will define the structures you will trace in real space. So down here, you see, for instance, like you have sort of, let's say, overdensity with a circular, cut. However, you have to imagine that this extends to a 3rd dimension. So actually, you would see sort of a filamentary structure with a circular cross-section. So what I'm going to do is I'm looking on what we call isosceles triangles. So these basically have the K1 and the K2 vectors have the same length, and we will vary just like the K3 vector. So, and just to give you an idea, what these 3, the squeeze, the equilibrium, stretch triangles look roughly their fluctuations in real space. This is shown by the color-coded plot here. And you can see for the squeezed one, this would result sort of in filaments with an elliptical cross-section. Equilateral are filaments with circular cross-sections, and stretch triangles. If you go to the really stretched triangles, you basically are probing planes. Then the other thing you notice that the bispectrum can be positive or negative. A positive bispectrum means that you have so that these concentrations here, they are above average. So you have above average concentrations. While if the bispectrum is negative, then you have concentrated below averages. So in terms of the 21 centimeter signal, if we have here the 21 centimeter signal map, then you could say that the neutral regions will provide the contribution from the neutral region will have a positive contribution to the bispectrum, while the contribution from the ionized region will provide which contribute negatively to the bispectrum. If we look now at this ionization field, we already can start to guess that our ionized regions are rather circular. So probably our bispectrum will be, if we look at triangles which are equilateral, will probably be negative. It will be dominated by the ionized regions. And this is exactly when we start plotting it. So what we're plotting here is now, we're still talking about isosceles triangles. So K1 and K2 vector have the same length. And then in this plot, basically the 3rd vector, we have here basically large to small scales. So that is in real space. And here you can see sort of the shapes in real space there would correspond to. So what we are seeing here is indeed what we already thought, like if we have equilateral shapes, our bispectrum will be negative. So here again, to remind you, everything is negative is dominated by ionized region. What is positive is dominated by neutral regions. And what we find is that on very small scales, the bispectrum is positive. On all other scales, it's mostly negative. And as reionization progresses, so as the universe becomes more ionized, this sign change shifts to larger scales. So how can we understand this? So there we are going back to the plot. Basically, I showed you before about the size distribution.
You have 5 more minutes, Anne.
Oh, thank you. The size distribution of the ionized and neutral regions. And so here you see again the peak of the size distribution of the ionized region and here of the neutral regions. And here I indicate basically what I call the bispectral scale. So that's basically the size of your K1 and K2 vector. And what you can say now, what we find, basically we have sort of 3 regimes. So in the first regime, you can imagine that the shape that your bispectrum traces is larger than the typical size of your ionized regions. And as long as this is the case, the sign change of the bispectrum traces the typical size of the ionized regions. Then at some stage, the typical size of the ionized and neutral regions will be larger than what you're tracing with the shape of the bispectrum. So it will be insensitive and you will have it at a fixed triangle shape, you will basically have the sign change. And at some stage, the neutral regions will become small enough that they basically fit into your chosen triangle shape. And you will start become sensitive to the neutral region. So your sign change basically will shift towards more equilateral triangles. And this is exactly what, if you summarize it here, so in the first thing, your sign change traces how the ionized bubbles grow, the typical size of the ionized region. Then in the middle one, it remains roughly constant around a fixed triangle configuration. And then as the abundance of neutral regions rises and becomes sensitive, it will move more towards the equilateral triangles. But how will this distinguish between different ionization topologies? That is basically, if we go back to this plot, we can say, all right, if we have like larger ionized and neutral region, then basically the peak of the size distribution of the ionized and neutral regions will shift to larger scales. And what this will result in is that the times or the average neutral hydrogen fractions at which you are in which regime will change. So basically the regime in which you're tracing the typical size of the ionized regions will be shorter. So you will enter the second regime far earlier. However, you will also leave the second regime where the sign change of the bispectrum remains rather at a fixed triangle configuration. You will leave that later at higher, at lower average neutral hydrogen fraction. And this is exactly what you will see. Now, if you plot all the bispectra, so what you see here is color-coded is basically the average neutral hydrogen fraction. So completely neutral universe is in blue, and then we go towards an ionized one in red. And here we have basically, the left panel shows you the results if you have rather ionized, smaller ionized and neutral regions. And as you go towards the right-hand panel, the typical size of your ionized and neutral regions will become larger. And what you can directly see is that if we are having larger ionized and neutral regions, we see that throughout a larger range of average neutral hydrogen fractions, the bispectrum will basically change its sign at pretty much a similar triangle configuration. However, if this is not the case, the triangle configurations at which the bispectrum switches its sign will be far more spread out. And this is, I think, a really nice sort of distinguishing tool, because detecting a sign change might be easier than detecting like an amplitude. So to summarize, is that sort of, I think the bispectrum provides a really valuable tracer of the ionization topology. And as I have shown or showed you, that it depends strongly on the size distribution of the ionized and neutral region. We have identified 3 regimes, and I think the most promising one is probably the one during the early stage, where really the scale at which the sign change appears tracks the typical size of the ionized regions. However, also when the bispectrum enters or leaves a certain regime, will also tell you something about the size distribution of the ionized and neutral region. And yeah, thank you.
Thank you very much, Anne, and thanks for keeping so very strictly to time. It was almost to the second. Excellent. So the floor is open to questions and comments. Who may I give the floor? Questions or comments? Well, if I may make my privilege, use of the chairman's privilege, then, and I mean one of the things that I remember was quite an issue a while ago in this bispectrum is just basically the compute power needed to do it, and that one of the reasons for considering these special cases is just that it makes the problem computable. How are we doing with that? Are people coming up with cleverer ideas of generalizing this to all configurations? Or are there also like special physics reasons to consider these special configurations of the case?
I mean, starting with these configuration was, I think, just one way to start off and actually exploring it. I mean, there has been now work where people have looked really at all unique triangle configurations. So that is definitely being done. Yeah, I think for me, the case was that I started off because there was already some work done on these ones. And so I could verify that I get similar results as they do. And then starting off there, to analyze how it is linked. No, but there definitely having been developed methods like how you can speed up sort of your bispectrum calculation. So it's mostly now via a smart way of Fourier transforms, and it goes actually now rather quickly to compute them.
Okay. Good. There is a question from Nicole Barry, and the question is, are the results independent of the normalization used?
So what I showed here are the normalized bispectra. So that basically means that you remove all the amplitude part, which would come from, let's say, also the power spectrum. So this is really the pure non-Gaussianity. I mean, of course, if you would add, if you look at the actual measured bispectrum, then you would need to multiply by the power spectrum. And then, of course, you would be also, dependent on your power spectrum.
Okay, good. Thank you very much. I see no other raised hands. Oh, there's a thanks from Nicole. Great. So in that case, I'd like to thank you very much, Anne, and I'll clap on behalf of all of us. So thank you very much. And then I would like to invite Anastasia Fialkov from the University of Cambridge to give her presentation to us. And Anastasia is going to talk to us about high redshift radio galaxies, a potential new source of 21 centimeter fluctuations. Anastasia.
Thank you very much. Do you see my slides?
Yes.
Yes. Okay. Thank you very much to all the organizers for giving me the opportunity to present this work. I realize it was very competitive this time. And I will talk about 21 centimeter signal and the new source of fluctuations that we recently added, which could be contributed by radio sources. So not do too much of an introduction. I'll just show you this light cone of 21 centimeter as the universe evolves from dark ages on the left to the end of the epoch of reionization on the right. We see that 21 centimeter undergoes a variety of changes. And sorry, I don't have a color bar here, but at dark ages, it's very small due to the coupling between the spin temperature and the temperature of the background radiation, which in this case was the CMB. And then with the emergence of sources of Lam alpha radiation, they couple the spin temperature to the temperature of cold gas. And we start seeing the sources in absorption. So on this map, we see bubbles of Lam alpha coupled gas in blue over the yellow and orange background. And then the sources, they're of course non-uniformly distributed around the sky, imprinting fluctuations in the 21 centimeter signal. Same happens with sources of ionization. They create ionized bubbles, as we just heard from Anne. and also X-ray sources such as X-ray binaries, byproducts of star formation, they would hit the cold gas in a non-uniform way, imprinting fluctuations in the 21 centimeter signal. So overall, we have a very rich of fluctuating signal over redshift and space. So conventionally, three types of fluctuations are discussed. There's Lyman alpha coupled bubbles, and then hot gas, as I mentioned, also imprints fluctuations in 21 centimeter signal, and of course, reionization and timing and scales on which this information is imprinted vary between all three sources. Typically, Lyman alpha happens first and dominates the transition from dark zone, and then X-ray heating starts heating up gas in non-uniform way, and later reionization is contributed, it is powered by more massive galaxies. Here we considered a signature of radio emission by sources in galaxies, and such sources or such contribution to 21 centimeter signal was previously discussed only in a uniform case when a radio background was added homogeneously around the sky, was uniform. While in our work, we looked at what happened when this radio background traces actually distribution of star forming regions. So we found, as I will show you in this talk, that this sets a new source of fluctuations that can have important observational implications. And we considered two types of signal. Well, that's the same model, but for a normal radio emission, such as produced by galaxies today, we do see interesting signatures at high redshifts, and then we also considered extremely strong radio sources that could explain the recently reported EDGES signal. So a bit of background, what we normally consider in 21 centimeter modeling is that the radio background is contributed by the CMB, and then usually gas is colder than the CMB at high redshifts, and the 21 centimeter transition imprints absorption feature over the CMB spectrum. And when the gas is heated, so overall observers would see distorted CMB spectrum, and if we subtract the background, we would see the what we usually plot, this global 21 centimeter signal with absorption peak at cosmic dawn and emission feature during reionization. And of course, this signal also fluctuates around the sky. So in our previous works, we varied astrophysical parameters for this model in very wide ranges and came up with this scans of this variety of signal for global signal and power spectra that really populate a vast part of the space in this gas temperature versus frequency diagrams and fluctuations versus slide. However, these models are inconsistent with the EDGES observation, and people came up with different models that can explain it. For example, adding dark matter interactions that would cool gas, or extra radio background that would create extra signature. So consider adding extra radio background, and in a nutshell, we just raise the temperature of the background, as you can see here with this blue dashed line. And what it creates is that it results in a deeper absorption feature during cosmic dawn, shallower emission feature, and later in the absorption and emission. And of course, it has also implications for the power spectra, which I will show you later. So in our model, radio emission is proportional to star formation rate in galaxies. Here, it's in agreement to what is observed today in low redshift galaxies. And we parameterize this relation between the emission and star formation rate by a constant called F radio. So for normal local galaxies, it's close to 1. So in this case, this extra radio background will trace star formation rate, and it will also fluctuate around the sky, and it will affect 21 centimeter signal around each source, but in an extended patch around it, so with some effective horizon. This background also evolves with time. And in this work also detects the new effects which tend to be important for cold scenarios. So three main effects of adding this extra radio background is, first of all, it creates larger contrast between the background and gas temperature, leading to deeper signals. That's the major effect of it. It also suppresses couplings because in spin temperature, all couplings are by the background temperature. So these coupling coefficients become less efficient and the coupling transitions last longer. So it takes longer for 1 centimeter to become coupled to gas temperature, and the collisional coupling takes longer. And finally, this effect also contributes to radiative heating, which in normal scenarios is up to 10% at redshift 17. So including this extra radio background increases radiative heating. So first of all, let's look at the map of Lam alpha coupled bubbles in these two panels radio background. So if you average radio background over space, it's the same number. But on the left plot, it's indeed uniformly added contribution to the CMB. And on the right plot, this is a case where radio background traces star formation rate, so it's non-uniform. These plots are shown at redshift 22, and color code represents the magnitude of the 21 centimeter signal. So we see that indeed adding extra radio background that is sourced by galaxies imprints stronger Lam alpha coupled bubbles around each galaxy. This would be easier to observe by, say, SK, and yeah, there is more homogeneity and fluctuations in this case. Looking at the power spectrum here, I show extreme cases of strong radio to just make this effect more apparent. We see that compared to the standard case, which is just CMB only case, the bottom dashed black line on this plot, fluctuations. And here I again show the case of uniform background, extra radio background with dashed lines, and fluctuating radio background with solid lines. So of course, the main effect, as I mentioned, was just to boost this contrast, and therefore it's strong both in uniform and non-uniform cases. But there is also signature of this non-homogeneity in radio background, because we see a difference between dashed and solid curves, which is quite strong, especially at the redshifts between 25 and 15. We found that these radio fluctuations, they actually correlate positively with Lam alpha, and therefore we see enhancement at cosmic dawn between redshifts 25 and 20 when you compare uniform radio case to the non-uniform one. And they anti-correlate with heating, so they kill each other, this types of fluctuations. And of course, the effect is model dependent and depends on X-ray spectrum, stellar mass, minimum velocity of halos, and so on. So let's first look at the case of more normal galaxies with small values of this radio protection efficiency coefficient between 1 and 100. And we see that in these cases, for example, for a radio of 10, there is a significant effect on both the global signal and the power spectrum. And most importantly, I think that the fluctuations during the epoch of reionization are boosted and could be easier to observe. In these cases, of course, radio galaxies also contribute to the just redshifted radio background that can be observed today, for example, by experiments such as Arcade, LWA. But for this normal radio production efficiency, this radio background is actually below their detection limit, so it wouldn't saturate and wouldn't corrupt any observations that we already have, just adding power to the high redshift 21 centimeter signal. And also these values, the normal values of radio production efficiency, are too low to explain the edges detected signal. In this paper, we did a parameter study varying properties of sources.
You have
and
5 more minutes, Anastasia.
Thank you, that's perfect. So we varied the properties of sources and looked at what kind of populations can have important implications for this by imprinting extra radio signals. And the models in which the signatures are high have high star formation efficiencies, low minimum mass of star forming halos, and also low X-ray efficiencies. So for such models, we find that even if radio of 1 to 10 would create about 10% effect in the power spectrum and the global signal. We next looked at extreme cases which could explain the edges signal. And this panel shows the global signals which could fit edges and color coded with respect to the redshift at which they would over predict arcade background. So such models have to be truncated in order to be consistent with observations that we already have. And these sources could only exist at high redshifts. And we assume that at later redshifts, population change and become less efficient in producing radio. So such signals would be very deep compared to normal cases shown here in the magenta line. This is an amplitude of standard astrophysical scenarios. And the amplitudes can be really deep, actually high. So again, we did a small parameter study to see what kind of astrophysical properties such sources would have in order to explain the edges signal. And these two panels on the left show the value of F radio versus X-ray heating efficiency, and also minimum mass of star forming halos versus total radio production efficiency. And we see that the models that could explain edges have very small halo masses below 10 to the 8 at redshift 17. They have low X-ray efficiency, which is needed to have deep absorption features. They have high estimation efficiency, which is required to enable the line alpha coupling at high redshifts, and also we need strong enough radio amplitude, but not too strong to overpredict the arcade and eldations. So we find quite a bunch of these sources existing there in simulations. An interesting feature is also that there is sensitivity to spectrum of X-ray sources, and for hard sources, we can allow higher X-ray efficiencies, well, because they're overall less efficient in heating up the gas, while soft sources need to be weaker in X-rays in order to have this absorption trough at the right place. An interesting implication is that if we add these galaxies that produce radio, they will also affect not only the global signal, but also the power spectrum of the 21 centimeter signal, which can be observed by already existing telescopes such as LOFAR and NANUFAR, that's SCAMBA and HERA. And so there is a one-to-one correspondence between global signals and power spectra. So if such is detected, we can see if it's consistent or not with what I just reported. This is a panel I adopted from Florent Martin that shows the potential detection space of NANUFAR that is coming online. And NaNoFar will be sensitive in the interesting redshift range to confirm or disprove edges, and it will hopefully become a. And just to summarize, we looked at some radio models and the recent LOFAR upper limits, and actually these models can be already ruled out. Part of it can be ruled out with LOFAR at redshift 9.1, and also with MWA. We haven't done it yet, but it's in the pipeline. These are not the same models that would create strong signals for edges, because these models need to peak at redshift 9, where edges signature has to be strong at redshift 17. And then we could also come up with a lot of eyes of LOFAR. So stop here with my conclusions. So I showed you that we have added a new source of fluctuations in the 21 centimeter simulation, which comes from non-uniform radio galaxies at high redshifts. Signature of normal population can be strong, up to maybe 10–20%, and has to be included in modeling of the high redshift populations and parameter inference. And this type of models provides new I just reported signal through power spectra and also direct count of radio sources. Thank you very much for attention.
Okay, thank you very much, Anastasia. Thank you. I'll clap on behalf of all of us. Michiel Brentjens has a question, and I'll unmute you, Michiel, so you can ask it yourself. It's a bit of a lengthier question. Michiel, go ahead.
Unmute. Yes, can you hear me now?
Yes.
Good. So in your comparison between your predictions and edges, the amplitude seems more or less in the observed range, but the shapes that you see in the spectrum are more or less parabolic or smooth on the bottom side, whereas edges sees this flattening at the bottom. So what do you think is necessary to flatten the curves in your predictions to look more like the edges spectrum?
Thank you very much for the question. I think adding extra source of X-rays could help to flatten it, or given more time between line alpha coupling saturation and the turn on of X-ray sources could also be helpful. We haven't done that because it's still uncertain how reliable the shape is, right? And it takes a lot of time to play with the models and fine tune, and we were just waiting to see what observers have.
Yeah.
Okay. Thank you very much. And I think in the interest of time, Anastasia, I'd like to thank you again for your wonderful talk. Thanks very much.
Thank you.
And I would like to invite Isabella Carucci from CA Saclay to take over with the next presentation. And Dr. Carucci will talk to us about 21 centimeter intensity mapping, addressing the foreground subtraction with a sparsity-based method. Take it away, Isabella.
Okay, thank you, Ralph. Thanks for the organizer for making this possible. Can you see my screen and my cursor? Is everything all right?
Yes, we can.
Okay, great. So yeah, I will talk about foreground subtraction with the method based on sparsity, and the work I'm going to show was done with the Melis Irfan and Jérôme Bobin, still at the CA in Saclay, close to Paris. And all the plots that I will show, unless stated, will refer to this paper here. So it's foreground subtraction for 21 centimeter, but I will focus on post-reionization intensity mapping. So we're not looking at the signal from EOR, but still it is interesting to perform such surveys with the idea that after UR, all the H1 that is emitting 21 centimeters is clustered in the galaxies, in the denser environments. And so by performing intensity maps of it, we can study the large scale structure of the matter and do cosmology with it. And indeed, it's a technique that is taking, there are instruments worldwide that are either already carrying out such a survey or planning to do so in the future. So it's something where there is some enthusiasm about. And indeed, already 10 years ago now, we got the first detection of this signal at redshift 0.8 with the GBT in cross correlation with galaxies, and more recently also from the Parkes telescope we got the detection still with galaxies. And the fact that these two detections have come with the help of galaxies is also like a smoking gun of what's the problem with this sort of signal. It's really hard because of foregrounds, especially, and systematics that we don't know. Indeed, here I'm plotting. There is a plot still from the GBT collaboration, the power spectrum of what they measure, or the thing they measure, together with this solid line here, which is the level of the foregrounds they are dealing with. So you see that it's order of magnitude higher, as also for the UR signal. So in terms of brightness temperature, this is what's going on as function of frequencies. This solid blue line is the signal that we like to measure, and here on the top you see all the galactic and extragalactic emissions that we need to take care of. So how did these people manage, this collaboration manage to get something out of it? Either with a sample polynomial fitting or PCA, but still they did acknowledge that it's not enough. There are things as the polarization leakage, I will come later also to this, that couple with the foregrounds and make the removal of these foregrounds really hard to perform with these standard techniques. Yeah, so they mentioned this polarization leakage that according to some models should look like this line here, this pink dashed line here. So it's something that is not as intense as the galactic foregrounds, but it's really oscillating, and it has a no-smooth behavior in frequency. And moreover, here I plot the same contribution polarization leakage as function of line of sight, so for different pixels, and you see that it changes a lot also spatially from line to side to line to side. So it's really hard to try to linearly take out this component from the data cube. And so we performed some studies without this, with this component, and also with component for the first time to start to check whether if we can remove it. So this is the components of our simulation. We have the emissions from the galaxies that we model with the Planck sky model, point sources, and this polarization leakage. And this is how the signal from 21 centimeter looks like in these same frequencies. And we try to perform the foreground cleaning using sparsity. So what is sparsity? A signal is sparse when it can be represented by very few coefficients. The usual example is the Fourier domain for waves. For a sine wave, you just need one number, the frequency, in order to describe it in Fourier domain. So the signal is sparse in the Fourier domain. So the idea is that if you manage to find a domain in which your sources are sparse, then their mixture will be less sparse than the sources. So this is where we start from with our data cube with 21 centimeter and foregrounds. If we manage to find this domain, then to go back and find the sources, we need to impose sparsity. And this will help the solving for this mixture. So in our context, where are the sources sparse? So how do I define a sparse solution for this synchrotron, for instance? So this is how the histograms of the in pixel space looks like for this image. If I move to wavelet domain, this is how it looks like. It is much sparse indeed. So this is why we chose to work in wavelets for this problem. And of course, it is more complicated than just few coefficients and to make up the mixture. It's something looks more like this. So basically, the idea is that different sources will have different coefficients in this domain, and it will be easier to disentangle in this way. And of course, it's not just few coefficients, everything else zero. We have some threshold, like a sparsity threshold, that still it's not defined a priori, because we can define it by looking at at the absolute deviation, for instance, of the coefficients. And this is how GMCA is built, so generalized morphological component analysis. So once you write down your signal in this linear way with a mixing matrix and times a number of sources, then you find iteratively A and S by using this cost function. So besides the usual data fidelity term, in order to check that you're getting the solution as best as possible, as close as possible to the initial data, you also impose sparsity to the sources in this wavelet basis at the same time. And it's already been used in some other astrophysical context. So we use this GMCA in our simulation for the 21 centimeter. And if I look at the how well we recover foregrounds, it looks great, sub 1% level, and I can recover the full sky of all these galactic and extragalactic foregrounds. However, this stuff is really challenging. Indeed, if I look at the signal that is left after my GMCA reconstructions on the light, GMCA residuals, you see that I do recover the input 21 centimeter noise, although I do miss some structure, especially at the, in regions where I don't have bright spots. So being more quantitative, this is I'm plotting here in these panels the relative difference of the angular power spectrum of the true minus the clean over the true, average over all the channels that I'm using. And these three panels represent three different ways of chopping my data cube. Here I'm showing how I do it. So basically it's number of channels and of course the thickness of channels that is changing from left to right. And this is to show that the number, the higher the number of channels that the GMCA can work with, the better for the reconstruction. So we can have a reconstruction of the true signal with less than 2% bias in angular power spectrum with just 3 sources. So this is good. This is the same sort of plot, but looking at the power spectrum in the line of sight direction. So the one-dimensional power spectrum, it's again, it looks good for 3 sources. It looks better for more channels. It's really around, it oscillates this relative difference around 0 up to some large scale in the line of sight direction. And this thing of having that, like the more the channels, the better, can be seen also by looking just one single channel, as I'm doing here. So this is the angular power spectrum for the same channel. Like I picked this 1097 megahertz on left and on right. With blue is the input, and the crosses in orange is what I get with GMCA. But here on the left, GMCA is run on 200 channels, and here on 40. And you see here where I plot the leakage of the cosmological noise in the foreground part and the leakage of the foregrounds in the residuals part, how things improve going from 40 channels on the right to 200 channels on the left. Here I see that I still have, like especially the synchrotron starts to peaking to increase how much synchrotron is left in my residual part of the decomposition. One other thing that we did in this exercise was checking for the issue of RFI. So basically, I don't need to explain here what RFIs are. We are all work with radio observations. So for instance, this is an image from some meerkat observation at these frequencies. Roughly 40% of the channels are thrown away because flagged out. And we try to simulate the situation with our data cube in this way, removing 40% of the channel in a symmetrical way, in an asymmetrical way, and then something that resembles what we are actually getting with meerkat. And this is the results for GMCA, still for 3 sources, and still in this difference, relative difference in angular power spectrum and in the line of sight power spectrum. And you see that we still get something that is that we are happy about. Like the RFI issue is not compromising the reconstruction by GMCA. And for instance, if with the same exercise done with the fast SEA doesn't give the same results, it depends on the RFI scenarios I'm looking at. I need to increase the number of components from 4 to 5 in order to get something consistent. Also in the line of sight, things are do not look so smooth. So this is a point for GMCA. Then we added polarization leakage, this very troublesome component that I was discussing before. And indeed, things need to be start to be more complex. Like here on the left, it's again the relative difference in angular power spectrum. I get something around the 10%, at least there's some up to some cutoff in the large scales. Although you can see that I need to increase a lot the number of sources that I'm playing with, and this means automatically that I'm also throwing a little bit of a cosmological signal away. Things improve a little bit, like I can push this reconstruction to larger scale when I start to masking regions where the polarization leakage behaves worse in frequency space. This is a comparison with fast SEA that to show that the GMCA has problems with the large scales, but for the small scale seems to be good at recovering the foregrounds, and so having back the residuals that we would like to measure. Another way of looking at this, so this is just for one channel. Again, in blue is the angular power spectrum that of the cosmological signal and the noise. Here, GMCA was run with 6 sources, on the right with 18 sources. And you see that this is on the bottom panels again, it's the leakage of the foregrounds in the residuals. And you see that it's not only
Vera, you have 5 more minutes.
Great, thanks. It's not only the leakage that is hard to remove, but it's coupling also with the other foregrounds. Also the synchrotron in purple here, they used to be under control with 3 sources. It's not more the case when we include polarization leakage. So it mixes up with all the other foregrounds and makes the situation more complicated. And these are my conclusion for this study. So we perform the GMCA cleaning on some simulated 21 centimeter in intensity mapping data. We measure the angular power spectrum with the 2% bias, and sub% level we can recover the radial power spectrum. So this is comparable or better than literature. What we did for the first time was, first of all, starting to playing also with the RFI contaminated data cubes, and good news, we got something like GMCA actually in a mixing matrix that has jumps in the frequency, like it realizes that there is a discontinuity in the data and it fixes for that. We also, for the first time, included something that resembles polarization leakage. And well, the situation started becoming more complex. And I think this is the take-home message of our exercise here, that we need to start accounting for more complex components in the data in order to test these algorithms. So we just started. We are doing more, like here I've shown results in full sky or with some masking, but now we're working with patches, and according to where the patch is, of course, there are different levels of sparsity we can rely on, so the results are different, and sometimes GMCA won't be the optimal method according to where you look in the sky. We started to look at the beam. Here I've used a Gaussian beam, but the beam has side lobes, so it adds also more complexity to it. And we are thinking about try to break down in scale the GMCA approach. Since thanks to the wavelet filtering, we can have a different mixing matrix according to different scales. So we can start playing around GMCA on small scale while it performs good, and maybe coupling it to other methods at the larger scales. Do I have some time left? I think a couple of minutes.
You have 2.5 minutes.
Okay, great. Then I will also give you a teaser of something that we are doing with the beam, because I think it's really, it's maybe more compelling for EOR studies than post-EOR studies, just because the beams are larger, or you even have to work with visibilities. It's also part of it. And so what we are trying to do is extending GMCA. There is already a version of GMCA called DAC GMCA. It's a work done by Jim Ming in 2017. So basically, the idea is that instead of, like here, I'm showing a simulation of EOR signal at 3 different channels, frequencies, and you really see here the effect of the beam going to the lower frequencies, how it looks like, just visually. Usually, to perform a PCA or GMCA or fast SEA, all these sort of component analysis methods, you need to bring all this, all the data cube at the same resolution in order to have something that makes sense. But indeed, you're missing information in the scale, in the channels in which the resolution is better. So with DEC GMCA, we are trying to do the GMCA part of the algorithms at the same time of the deconvolution in order not to lose information. And this is how it looks like, where I have my input. This is my two-step deconvolve via GMCA, and this is this DEC GMCA solution. And this is how the residuals look like. So here, it does look more like the EOR signal should look like. Here, there is still some leftover large-scale structure feature that probably come from this the convolution step. And things are even more dramatic when I go to lower frequencies. Here, the residuals in this case. And this is something that Remy is doing in our group. He extended already, here I highlight his paper. He extended already this DXGMCA to work on the sphere with spherical data. And he wants to proceed with working with the visibilities and so on. He's working on it. And okay, I'm done. Thank you.
Okay, thank you very much, Isabella, for again keeping very well to time. So once again, I'll clap on behalf of everyone for this beautiful talk. And I would like to open the floor for questions and comments. Well, if I may use the chairman's prerogative, and I warn you, I do not work in this field. You have not seen my name on any EOR papers. One of the things that I noticed that, of course, a lot of this is still preparation for things to come. So, I mean, how close are you to actually getting data that you could test this on?
Well, with the Meerkat in intensity mapping, we are actually already testing these things. FastSCA has been used. Well, also on GBT data, FastSCA has been used in WALS 2017. Now, these methods have been used on data. We are talking about post-reionization, so below whatever is below redshift 6. In the case of the instrument, still around redshift 1 or below, but there is data already. And yeah.
Okay,
something
great.
That is happening.
Okay, thanks. So Michiel Brentjens has another question. Michiel, can you unmute yourself and ask the question?
Yes, I have unmuted. So thank you for this talk. You require spatial sparsity, and I did not exactly get if you also required sparsity in the frequency domain. And I understand you run into trouble with polarization leakage, and I was wondering if that is due to the spectral structure of polarization leakage or due to the spatial structure of it.
Yeah, indeed, it's the frequency structure polarization leakage that is more troublesome for GMCA because we impose sparsity just on the spatial domain through wavelets, yeah. And we don't include any sort of priors or assumption for the frequency domain. So probably with something like polarization leakage, we need to start assuming something on frequency. So but you're right. Yeah.
Most of it would be the Galaxy, I presume, and there you would see leakage from Stokes Q to Stokes I, and so I would expect something that scales with more or less lambda squared, compatible with the foreground Faraday rotation or something like that. So
yeah, we try to exploit this lambda square relation property of the leakage by doing a different binning and try to run GMCA on data that was binned in the way to respect this lambda square property, but we didn't we didn't include it in the final study because we didn't. I mean, it was not better. So I really think that a prior in the frequency domain will be necessary in order to perform a proper cleaning of this component, or we just do some cut off in K and L space, or but GMCA as it is right now cannot deal with this component.
Okay, thanks very much. I'm sure that will lead to some interesting offline discussion. So
Thank you for the question.
yeah, thanks very much again for your very interesting talk and answering of the questions, Isabella. So once again, my applause. Thanks very much.
Thanks.
And with that, I think we turn to a pair of talks from Imperial College. So that's interesting. So I'd like to invite Ian Hothy. I hope I don't mangle your name too much, Ian, there from Imperial College, who will speak to us about comparing foreground removal techniques for recovery of the LOFA EOR 21 centimeter power spectrum.
Can you see my screen?
Yes, I can.
I'd like to thank the RAF for introducing me and the organizers for letting me speak today. My name's Ian Hothy. I'm a third-year PhD student at Imperial College in London, and I'll be presenting work from my recently accepted paper into the MNRAS of comparing foreground removal techniques for the recovery of the LOFA EOR 21 centimeter power spectrum. There have been many good overviews of the EOR, so I'm going to refrain from going over it again. But I will discuss the foreground problem. So as Isabella mentioned, that there are several foregrounds that contaminate this 21 centimeter signal we wish to observe. These come from both our galaxy in the form of synchrotron emission and free emission, as well as extragalactic sources such as radio halos, radio clusters, and radio galaxies. And these kind of exacerbate the problem of trying to already find a weak 21 centimeter signal, because the foregrounds are several orders of magnitude stronger than the 21 centimeter signal itself. And so it turns the problem of finding a needle in a haystack to finding a needle in the field. Luckily, we have a range of mitigation techniques at our disposal. These typically fall into two schools, foreground avoidance and foreground removal. On the left here, we have the cylindrical power spectrum. So it's the power spectrum bend along the line of sight and angular, producing these kind of jewels of the K parallel and K perpendicular respectively. And so due to the chromatic nature of our instruments, the fact that their response changes with frequency, we end up getting the foreground wedge. And within this foreground wedge should be our intrinsic foregrounds that I just mentioned, as well as any calibration errors or any other instrumental effects. The corollary of having a foreground wedge is that there should be certain K modes in which it should be only the 21 centimeter signal and noise of our instrument. And studies that focus on foreground avoidance look at taking the modes within the EOR window to do their analysis. And the second school is foreground removal. This is where we look to model the foreground to subtract it from our data, and these fall into two categories. The first are parametric methods. So these assume the form of the foregrounds a priori. In the previous plot, you saw that the foregrounds obey a power law in the frequency domain. And so one can easily fit a smooth polynomial to the foreground and subtract it, because we know that the 21 centimeter signal is a highly fluctuating signal, and so wouldn't be picked up by the smooth polynomial. And the second are non-parametric methods. Now, non-parametric methods assume nothing of the data a priori, and this has a few advantages. As you've just seen, again, as Isabella mentioned, for example, you might get polarization leakages. You also get the mode mixing due to the chromatic nature of the instrument. And these can lead to highly fluctuating signals that parametric methods such as polynomial fitting can't pick out. And so non-parametric methods use the data to model the foregrounds. An example of this is fast ICA. For the analysis done in this paper, we use foreground removal. Just in case in the last 4 minutes you've completely forgotten blind source separation techniques, such as GMC, I'll give a brief overview. So the observed signal, so the signal we wish to observe, is composed of a foreground model. And as Isabella said, it's made up of a mixing matrix and a source model. The source model is a column matrix where each row is a different foreground. In an ideal world, the source model is each row in the source model is each of your different foregrounds, and the mixing matrix is your identity. But of course, in reality, it's far from perfect, and your source model becomes more of a mixture of the different foregrounds, and the mixing matrix deviates away from the identity. But once we have optimized our foreground model, GMC again does this through enforces sparsity through morphological sparsity. and FastSA does it through statistical independence. We can subtract the foreground model from our observed signal to get the Gaussian noise, which should contain our 21 centimeter signal and instrument noise. To show you an example of what the source model can look like, this is a simulated foreground, and then using FastSA to fit the foreground with 3 components. The main hyperparameter of these blind source separation techniques is the number of components or sources you wish to model the foregrounds with. And of course, here you can see that something, because obviously the galactic synchrotron is by far the strongest foreground, you can see it gets its own row within the source model, whereas the other 2 look like a mixture from free and extragalactic. The third technique we use is Gaussian process regression. This is what's currently used by LOFA and led to the most recent upper limits by Mercent et al. 2020. GMCA was used, and that was Patil et al. 2017. So Gaussian process is a probability distribution over functions. And much like a normal Gaussian, it's completely defined by its mean and covariance. And we represent the covariance with kernels. An example of a kernel is this Matern kernel. And you can see that this new parameter leads to different functions. You can see on the right plot here. And again, the main hyperparameter here is this L, which is the coherency length. So the coherency length of your signal. And so for us, it would be along the frequency domain. So we know the foregrounds are fairly coherent, especially over 50 to 100 megahertz, whereas the 21 centimeter signal is fairly incoherent and will have a coherence length of the order of a megahertz. And so we can decompose the overall covariance of our observed signal into the different components we know: the intrinsic foreground that I mentioned, the mode mixing due to the chromatic nature of the instrument, as well as the 21 centimeter signal. And we can decompose these into different kernels because they have different coherency lengths. And so we give uniform priors to each each component of the observed signal. So we give uniform priors to the coherency length, and we perform a Bayesian optimization to optimize it. And so where we currently stand in this paper, we want to compare these 3 techniques to find which is best for LOFA. And so the first thing that one might do is to apply it to the most recent data. And this is 140 hours or 10 nights worth of LOFA data. We use our own GPR almost as a sanity check to make sure we're doing everything correctly. And for FastSA and GMCA, we use 6 components or sources to model the foreground. And we can see that all 3 techniques recover the most recent LOFA upper limit by Mercent et al. 2020. And for the lower K values of our power spectrum, we see all 3 techniques perform pretty similarly. Though GPR does give slightly lower limits, GMCA and FastSA are not too far off. But by a value of K equaling to roughly 0.1, we see that FastSA and GMCA begin to significantly diverge from the GPR result. And so now the motive of the paper changes to finding what causes this degradation of performance at these higher K values. And so the first thing we might do is to attempt to emulate or simulate these kind of observed data. And so we know the frequency range of the data is 134 to 146 megahertz. So we can simulate this through 21 centimeter fast. We also simulate foregrounds in the same frequency range using that outline in Yelich et al. 2008. And we send this through OSCAR. OSCAR is an interferometric simulation, essentially applies the measurement equation. And we simulate this for 10 nights. And as we saw in the similar plot, in the previous plot, GMCA and FastSA perform quite similarly. So for brevity, we only show the results of GMCA. And we have 3 cases here. So in the first case, it's just a normal 10-night observation. So we simulate a normal 10-night observation. In the second case, we don't apply the primary beam. And in the third case, again, due to the chromatic nature of the instrument, the fact that its response changes with frequency, we use the lowest frequency, so 134 megahertz, PSF, and apply it to our entire bandwidth. And that effectively smooths over the data, removing mode mixing. So to reiterate, case 1 is just a normal observation. Case 2, no primary beam. Case 3, no mode mixing. And so we can see that three components fit the first case the best, and to give a direct comparison between the three results, we use three components for the other two cases. And we can see for case 1 and case 2, so the case where we don't have any primary beam, we can see that there are some differences, but they perform pretty similarly, both for GMCA and GPR, which makes sense because we emulate what we do in observations, which is we cut our field of view to be within the primary beam. For case 3, so for GPR, we remove the mode mixing kernel from our total kernel, and we can see that we get a slightly deeper power spectrum on certain scales. And interestingly for GMCA, again, we've removed a source of power, so we do expect to get a deeper power spectrum. But interestingly, 3 components becomes too many at the highest of K. So we begin to get overfitting at the higher K values. All of these power spectra have their noise bias removed as well. So there isn't, because obviously here we see at the highest of Ks, we see overfitting, but there isn't a single instrumental effect that we've simulated that is causing the degradation at K values higher than 0.1. And so, as you probably saw in Isabella's presentation, GMCA and even fast ACA are normally performed on hundreds of megahertz worth of bandwidth. Here we've given it 10. So we thought, okay, let's increase the bandwidth over which we perform these removal techniques. And so for GMCA and fast ACA, we see slightly deeper power spectra, but we see it across all K scales rather than just the highest of K. For GPR, we see a slight degradation in performance, and this makes sense because the coherency length evolves as we increase the bandwidth. And so when we try to fit to a larger bandwidth, we get like almost like an average coherency length, and so we don't get as good as a fit. So we haven't yet identified what's causing the degradation at K values above 0.1, but we see hints of it. The first thing you might notice is the simulated observation here. So for case 1, performs a lot better than the actual data, right? We get a lot deeper power spectrum with less components. And that makes sense because there are a lot of instrumental effects that we don't include, right? We don't see calibration errors here.
You have 5 more minutes, Ian.
Thank you. And also, Andrew Effinger showed last year that having flagging, so for example, during your time and frequency averaging of your measurement sets, as well as during your gridding, can lead to some excess power. And so this excess power would increase the power, especially at the highest of Ks. He did show ways of mitigating it, but it's more mitigated at lower K values. And interestingly, when we remove a source of power, so we remove mode mixing, we get overfitting at higher Ks. And that's because all of these extra instrumental effects lead to increasing the number of components at higher Ks. And we can show this. So we flagged channels during gridding to lead to this kind of excess power. We've slightly exacerbated the problem, so we've removed a third of our frequency channels. And so we can see this is the exact same data, except we've flagged in one case, and the other case is unflagged. And so this is flagging during gridding. And we can see with the same number of components, at the highest of K values, we start seeing underfitting. And so our residual value is higher, and we begin to see this excess noise, this excess power leaking into our residual. And so what in fact is going on here is due to the scale independence of our observed signal. So because, again, on the lower K values, 6 components works fine. We recover the same upper limit. But as we go to higher K values, all of those instrumental effects that we mentioned increase the number of independent components. And so the way fast ACA and GMCA works is if I say look for 6 components, it looks for 6 components at all scales. But we know that at the highest of K scales, we know that there are a greater number of independent components. And so 6 components no longer become sufficient to model the foregrounds. So you might ask, okay, why don't we just fit with the highest number of components we can? And the problem with that is you get to overfitting. And so this is, again, the cylindrical power spectrum, but it's a ratio of the fast IC and GPR results shown in this plot. And we can see that even with 6 components, we get overfitting on the lower K parallel values. So even 6 components seems to be too many. So to conclude, with the 3 techniques, we recover the most recent upper limits, but we see that the blind source separation techniques have the performance degrading with K. We find that no single instrumental effect is causing this, but instead is caused by the scale independence of the mode mixing matrix for the blind source separation techniques. And so we conclude that both for its current performance and its performance on the bandwidth we've given, that GPR is the most optimal. But this begs the question of whether we're performing these blind source separation techniques in the most optimal way. So again, we've talked about bandwidth. For the analysis here, we've given it, and even in the actual data, we've given it 10 megahertz of bandwidth, whereas you normally expect them to be performed on hundreds of megahertz. And also a more scale independent approach. Isabella mentioned it at the end of her talk, which is having a kind of multi-scale approach to GMCA. Of course, that begs the question as to like, how would you select the correct number of components for each scale as well? And finally, as of yet, we're not fully capturing the observational effects of the real data. Again, such as RFI flagging or calibration errors, or as Isabella mentioned, polarization leakage. And so if we don't do this, we don't really get a full understanding of our results, especially when we're applying our removal techniques. And I think I will conclude it there.
All right, thank you very much, Ian. Once again, applause on behalf of all of us for this wonderful talk. Clearly a lot of quite difficult work that went into that. May I open the floor for questions and comments, please? I see there is one coming up in the... So let's see, Nicole, can I unmute you and let you ask your question?
Sure. Can you hear me?
Yes.
Awesome. So I was fantastic work, by the way. I wanted to try to understand what is the least amount of flagging you can get away with while still not seeing too much excess power. So I was wondering if you tried to quantify with those RFI tests you did, if it was like a typical amount of RFI flagging, or if you plan on varying the amount that you're doing and seeing what kind of power you get out.
I will admit I didn't vary the amount of flagging I did. It was more of a sanity check to ensure that like my conclusion was right about it was potentially calibration errors or RFI flagging leading to a greater number of independent components. But I can imagine that as you have a greater amount of flagging, that you get a slightly exacerbated excess power. I know, so from the LOFA data, I think probably less than 10% of the channels were flagged, and I don't have an exact number to quantify the amount of excess power or how excess power changes with the amount of flagging. Sorry. But
Awesome. Thanks.
I would assume that it I don't know whether there would be like a minimum amount, but I would assume that obviously the less flagging, the better. But I don't know if there is a threshold. So thank you.
All right.
Great.
I also have a question, if I may. Having tried a lot of things for a Gaussian process fitting method in a totally different context, Gaussian processes can be a bit finicky in the sense that they have their own minds about what part of the thing you're trying to fit they should actually take up and how much to leave for the underlying model you're trying to fit.
Yeah.
So have you experimented with things like the scale lengths that your Gaussian process is allowed to have on that k-axis, and to see whether it makes a lot of difference in how much of the total signal it absorbs?
So I personally haven't done that analysis, but Florence Mertens did. It would have been, I assume that he would have done, it would have been in his 2018 paper, because I'm using his kind of GPR model. But they did test test a lot of the kernels, not only to find the optimal one, but also like how best to apply the kernel. So I would assume that they have done that kind of analysis, but I can't say for sure.
All right, thank you. Any other questions or comments?
Can I ask something from the panel? I cannot write on the
yes,
Q&A.
Isabella, please go ahead.
Yeah, so, well, really nice work, Ian. It was really nice to see that from totally different, coming from a totally different data set. I mean, at the end, some conclusions are the same as mine, of the scale dependence and so on. So I wanted to know whether you do something about the resolution of the data cube before running the, like you try to deconvolve to the same resolution, or you just apply the BSS on the data cube as it is. And okay, yeah,
we apply it just as it is. So we don't. So I mean, that was what case 3 was for our simulated data, where we give it a constant resolution. But for the actual data, we didn't do that.
Okay, right.
Okay.
And then yeah, when you say that 6, like how do you? How can you tell the number of components that are optimal for the cleaning?
So the first thing we did was I kind of based it on because it's like the minimum number of components you get prior to you getting significant overfitting. So after, if you use 7 components, we started getting the especially at the lower K values, we started getting significant overfitting. And so it wasn't done through like a statistical method, but more of like a by eye. Like I found that 6 components was best, or gave the least overfitting.
Okay.
Thank you.
Thank you very much. In the interest of time, I think we have to take the rest of that discussion offline. Thanks very much again, Ian, for your wonderful talk. And I would like to invite your colleague also from Imperial College, Thomas Binney, to take over now and talk to us about the Mollet power spectrum in 21 centimeter parameter estimation.
Hello, can you hear me okay?
Yes.
And can you see my screen?
Yes, we can. I can at least, so I assume everyone else.
Okay, well, thanks to the organisers for giving me the opportunity to speak. I'm Tom Binney from Imperial College, London, due to be finishing my PhD soon. And this is sort of a final chapter that I've been adding on recently, which follows on from work that Kath Trott and Stephen Murray have been doing. So to start with, I'm just going to give you a recap of the context where this is going to fit in and why it's important relative to the light cone effect, an introduction to what it actually is, and the sort of attempts of applications that we've been looking at so far. And this work is quite preliminary, so there aren't really any real conclusions, but I'll sort of look towards remedying what we've done so far and how to progress into the future. So to start with, parameter estimation utilizes Bayesian statistics, where we look to find the best fit parameters for a given model using a data set at hand. And throughout this, we'll be using uniform priors. So what we're really doing is trying to find the peak of the likelihood function. And this likelihood function is typically a chi-square between the 21 centimeter power spectrum. So just for basics, the power spectrum is the Fourier transform of the 2-point correlation function. And the correlation function is the excess probability for a Poisson distribution for any quantity. In this context, that quantity is the brightness temperature. And throughout this, I'll refer to what you're used to as the power spectrum as the Fourier power spectrum. And the FPS here specifically is the spherically average version, which is typically used in parameter estimation in codes like 21CMMC. So the power spectrum is a very useful tool in lots of scenarios. However, it isn't able to fully represent the entire light cone. So we have to take chunks of the light cone in order for it to be approximately ergodic within these chunks. And so we can approximate the statistics of that chunk as the light cone evolves. So even within these chunks that get taken, signal tends to be exaggerated from the far end and de-exaggerated from the front end, as there is evolution across the box, which we sort of try to ignore by taking chunks with the bandwidth. And this can be optimized as work by Data et al. Has shown. But to try and move away from this, we introduced the Morley transform, which is very similar in terms of its mathematical definition, but we replace the Fourier modes with Morley bases, which is essentially similar to the Fourier modes. It has a Fourier part, but these are all wrapped in a Gaussian envelope. So the way we use this here is by relating the width of these Gaussian envelopes to the perpendicular K modes and how they evolve along the light cone. So this proportionality symbol here will contain all of the cosmological constants that we're using. And we have one of these Morley wavelets along each sensor position throughout the light cone. And to see the basis and the foundation of this, please see Kath's 2016 paper, which includes definitions of the volume averaging that we use. So to give you a sort of recap / comparison of the methodology, we have our light cone, and to use the Fourier power spectrum in parameter estimation, we split it up into chunks, and we take the Fourier transform of the brightness temperature for each of these. With spherically averaged K, we get a power spectrum per K and one of these per redshift or per frequency band. In the Morley case, we do this per perpendicular mode, and we now have wavelets along the line of sight, which are each centered at different frequencies along the light cone. And so you get one of these plots per perpendicular, per centering of the light cone position and per perpendicular mode. But I'll come to trying to interpret this a little bit later. So now that we're trying to input this within a parameter estimation context, we need a likelihood function. So typically for the Fourier power spectrum, we take X as our sample and U as our data, which is simulated in this context. And the covariance that we use, ignoring cross-correlation terms within our light cone, essentially assuming that the K-modes can be independent, which in the context of us having our power spectrum approximately ergodic within the chunks is okay. And we can use a sort of a noise power spectrum, for example, 21 centimeter sense in this covariance matrix support. But now expanding this into a more general context, this is the full Gaussian model of the likelihood that is conventionally used. But now that we actually have our wavelets depending on the line of sight modes, we can no longer approximate our K modes as independent. So we need to take a full calculation of the cross-correlation terms, which after a very lengthy derivation gives this form, where we take the covariance of the wavelets within one light cone, and we try and have this sort of Gaussian suppression term that's related to the telescope noise. However, for now, as this is the early stages of this, we don't have any telescope noise, so this is 1. So applying this to simple EOR models, we do it in the context of 21 CMMC, as I've mentioned, with Brad Greek, one of the collaborators for this work. And we essentially have our brightness temperature relating to the neutral fraction and the density field. And we're using a very simple 2-parameter model. Within the light cones that we use, to start with, we tried to only use a short redshift range between 8 and 10, just to check it worked. And note that the light cone structure here is created by stitching coeval cubes together. So when modes extend beyond the size of these boxes, the properties are wrapped towards the edge. So the first result we looked at is what I've looked at is trying to cross-check the covariance equation that I showed you earlier. So the top row of these are examples of different K modes with the perpendicular modes averaged, increasing from left to right. In the top row, I calculated 1,000 light cones with 1,000 different random seeds and calculated the covariance between the Morley wavelets sort of manually. While the second row uses the equation on one light cone, so only one random seed. And the bottom row uses the same, but without this suppression, as though we've ignored the cross terms. So in the majority of the cases, at least while we haven't included telescope noise, there isn't too much difference between these. However, as the K modes increase and the sort of stitching structure is more visible, when we only use one random seed, the sort of almost penalties from sample variance for only having one light cone become apparent with this tartan structure. And this is where this suppression becomes important. So we sort of kill off any invented structure due to the statistics. So now applying this in parameter estimation, we used the simple 2-parameter model and ran an MCMC with about, I think it's exactly 8,000 points. And so both recover the posterior map value well, but importantly, the variance on both posteriors reduces by about a factor of 5 when we use the Morley power spectrum likelihood compared to the Fourier power spectrum likelihood. So this is a big win for the Morley power spectrum over the Fourier power spectrum. And sort of finally in the results section, but this is definitely the most open-ended, is trying to look at interpretation of the signals that appear. So to get a gist of how the properties are projected, I've simulated 5 different light cones, again in the same 8 to 10 redshift range, with parameters varying throughout the appropriate priors. And these are picked fairly randomly, but these third and fourth rows have reionization finishing unphysically early. And these properties are averaged in the plots below. All of them come from the same density field, so that's as expected. And firstly, I'll refer to the power spectrums of each of these quantities, where the chunks are created in these sort of shaded bands. And we're used to seeing the brightness temperature power spectrum here, where each of these sort of reflects the kind of relative properties within each band as expected. Although note that these sort of very small rows would typically be cut when this is used in any context. So trying to do a similar thing with the Morley power spectrum, I've taken the first of the averaged perpendicular K modes, and now I've plotted the perpendicular modes against the wavelets for each center position as the wavelet moves throughout the light cone. But there isn't much change along the light cone. And I think this is a testament to the modes being picked up consistently throughout the progression of the methodology. And similarly with the Fourier power spectrum, above a certain K threshold, you can distinguish well the different models' brightness temperature values. And this bottom plot is different from the top plot in that I've multiplied the wavelets by K parallel cubed to remove spatial dependencies. And the bottom one, where there is next to no neutral fraction at all, drops off the axes. The other way that I've tried to interpret plots is by plotting the centers as the wavelet moves along the light cone, then having a different plot per K parallel mode. And these reveal that further down the light cone, there is more signal, which I think you would expect, as our simple model only depends on the density field, which is the same for all of these models, and the neutral fraction, which increases at higher redshift.
5 more minutes, Thomas.
Okay, thanks. But really trying to interpret these is the tip of the iceberg. So these are slices of the entire data cube. And I think it's quite easy to say that this is a bit of a mess to try and interpret. But there is a lot of information encoded in these. And other than the 2 cases where reionization finishes unphysically early, they're fairly indistinguishable from the models that I've used. So we will really need to put more work into seeing how this behaves with different models and different parameter values. But as I say, these are very preliminary results, and this is sort of the tip of the iceberg from what appears to be a very promising statistic. So looking towards the future, experiences by about a factor of 5 in the same MCMC. However, this has been on a reduced redshift range. Importantly, if this was to be applied properly, it would be nice to try and recreate results like Brad Grieg's paper, where he compares light cones to coeval cubes in parameter estimation. However, trying to calculate 600 by 600 coeval cubes along a light cone that's about 20 redshifts long required terabytes of RAM per sample. And so we need to try and come up with ways to reduce that. One of these would be perhaps logarithmically stepping the wavelets through with higher density in areas of more interest. And the other being perhaps doing it on smaller chunks of light cone and then combining those. So I don't see a reason why you couldn't do that on smaller pieces and then stick it together later. But importantly, although it is hard to interpret, the Morley power spectrum does trace the brightness temperature, and it could be very useful in interpreting signals from the EOR. So looking to the future and sort of wrapping up, we would definitely like to include telescopes once we have this sort of data problem under wrap and understand a feeling for how the power spectrum evolves. And CAF has already implemented this on the MWA data. And this is what it looks like as an upper limit. Although considering that we don't really have a grasp on how the models move yet, although it is underway, this could be very good at furthering the constraints that people like Brad have done using the Fourier equivalent of this MWA data, which was able to rule out low heating models and cold reionization. But these are set to improve. And also, if we are able to utilize the whole bandwidth in one go, this could be quite groundbreaking for foreground mitigation techniques. If the signal structure is unknown, we rely on continuity between bins in some of these contexts. So being able to access the whole light cone in one bandwidth could be quite revolutionary. It should be available soon, hopefully. Thanks. I'll take some questions.
Okay, thank you very much, Thomas, for this wonderful talk. Let me again give you an applause on behalf of all of us. Excellent. So may I open the floor for questions and comments on this talk?
Yep, sure.
Can I ask a question from the panel?
Sure, go ahead.
So I have 2. So the first is different. Are you considering looking at different wavelets to see if there's one that's optimal? And the second is, how are you deciding the width of your current wavelet? Like I get that you'd, for example, mark that power spectrum limit to like 10 megahertz, for example, to stop too much evolution. But is there also a minimum size? Like if you go too small, it will be problematic.
So I haven't looked at a minimal size as of yet, although we derived this relationship between the width of the wavelets and the K modes from the sort of optimal bandwidth prescriptions that come from Data et al. There, I can, if you want further discussion of this, I can go through the proof with you later. But yeah, I can't really go into more depth of that quickly. Other wavelets, there is certainly scope to expand beyond just a Gaussian. But for simplicity's sake, it would be nice to get just the Gaussian to work on the entire light cone first before we head down that route. Ideas like using the Dulbechet wavelet that comes into use in certain foreground mitigation techniques would be quite an interesting application, I think.
Okay, thank you. Are there any other questions or comments? Going once, going twice, gone. Well, then I'd like to thank you again very much, Thomas, for your very interesting contribution. Thank you very much.
Thanks. And
with that, I would like to invite our next speaker, who is Hugh Garsden from Harvard-Smithsonian, and also our final speaker of this session, to talk to us about 21 centimeter power spectra at redshift 28 from the Owens Valley LWA. Hugh, take it away. Hugh, are you with us? Ouch, is it possible that we lost Hugh? You are muted.
Right.
No, there you are.
I think I'm right now. Yeah, okay.
Yes.
Right.
If you would share your screen. Okay, we see your screen now and your cursor.
Okay, we're going. Everything okay?
Yes, I think so.
Good. So I'm representing the LEADER project run by Lincoln Greenhill at CFA. I'm currently at Queen Mary as a postdoc. The work was carried out at CFA.
Thank you for that correction.
So the LEADER project is working towards a detection of global 21 centimeter signal. And there was some talks presented at the global 21 centimeter workshop about that. And also detection of 21 centimeter signal in power spectra. So we're working at high redshift of 15 to 46, which is a frequency 30 to 87. And that's because we're using the Owens Valley long wavelength array, which is in California at Owens Valley. It's an interferometer, plus it has some radiometers attached. This is a picture of the array. So there are 256 dual polarization dipole antennas on the ground with a max separation of 200 meters, which are the antennas used by LEADER. Caltech has other antennas that give a wider separation. I'll just go through our method for power spectrum generation, which is a delay spectrum method. So we start with the idea of observing the 21 centimeter signal in a box at high redshift. With the XY plane is the plane of the sky, and line of sight is observed by using different frequencies. The signal is isotropic, so there's no preferred XY direction. So we collapse X and Y to what I'm calling XY, and just Fourier transform in this square. There are other ways, obviously, of getting a power spectrum, and we've heard some of them. I just want to point out Mike Eastwood's work. He generated power spectra using M-mode analysis, which comes from spectral harmonics, and that was on Owens Valley data. In practice, using an interferometer, the correlation of the signal between antennas gives us the Fourier transform in the XY direction. So we go from this to this, where we get K-perp modes for free out of the interferometer. So we need to make the Fourier transform in the line of sight direction, but the interferometer does not produce values on a regular grid. And that is because we are observing using baselines, i.e. the antenna pairs and the separation between them. So in that box, we get values on these lines that come from the baselines observing at different frequencies, and they drift by K-perp. So to do a standard 2D Fourier transform, you would transform in one direction and then the other, but we can't strictly do the transform in the line of sight direction. Whoops, sorry about that. There is a way out of that, which is the delay spectrum method. So a lot of you will be familiar with that, introduced by Aaron Parsons a few years ago. So we just FFT the baselines. We FFT these lines of data. The advantage of the delay spectrum method is that it isolates foreground power in a wedge. The Fourier transform is a delay transform, and it produces power per delay. The delay is just the time delay between antennas in baselines of foreground signals. So we get this nice foreground isolation in the wedge. The effect on the 21 centimeter signal, which is embedded in the observations, is that we will approximate the line of sight spatial Fourier transform, which gives us the K-parallel modes. So this just shows a bin where we've got lots of baselines, assigned them the same K-perp, bin them here. Baselines are stacked from left to right, bins go from left to right, and the baseline length increases as you go left to right, the delay increases, so you get this expanding wedge. There's obviously other ways of doing foreground avoidance and removal, some of which we've just heard about. So this is our power spectrum. I'll just quickly go through some properties or facts about it. This is polarization XX, which is east-west. We do have YY. It's integrated from 4 hours of data, so that's each baseline observing over 4 hours, basically. The LST is 12 to 13. The only moderately bright source is Virgo A in the field. The frequency range is 43 to 53 megahertz, so that's a 10 megahertz band, which observes the 21 centimeter signal at 25 to 32 redshift. That corresponds to a time from the Big Bang of 100 mega years and a time range of 35 mega years. So we get our K-perp mode on the x-axis, K-parallel on the y-axis. We can also plot delays that are relevant to the foregrounds on the right axis here. The blue lines are the horizon, which is the theoretical wedge boundary. Power's on a log scale. It's measured as a temperature squared, milli-K squared, and from this we can extract the dimensionless power, delta squared, that's used for, that is familiar to people from CMB and often quoted. I'll make some comments now. There is a wedge, so that's good. There is foreground leakage outside the wedge, and there are artifacts outside the wedge. So there's a faint artifact here that drops as you go from left to right, and that's due to cable refractions. The 21 centimeter signal is buried in thermal noise and unremoved systematics outside the wedge. The systematics come from inadequate calibration, inadequately flagged RFI, hardware problems. So we do not claim an upper limit. This observation will give us a delta squared at about 10 to the 12 milli-K squared. That's way above the 21 centimeter signal expected value of the 21 centimeter signal at 10 squared, milli-K squared. Mike Eastwood, he found a level of 10 to the 4 milli-K squared. So that's far below what we've got, but that was 28 hours of data and at a different redshift. So I just want to, I'm going to zoom in something here just to point out a couple of features of the spillover. So it appears that there are two levels of spillover. I don't know if you can see them here. One just outside the wedge, and that is fairly common for wedge spectra. There are reasons for that, including putting a window function on the FFT can cause that. Then there's a second level of spillover at a lower level, and both of these track the horizon line. So they exist on both sides of the wedge, and at the moment we don't know what is causing that. So there are some issues or caveats related to what we've done. The Z range that we've used, 25 to 32, is really too wide because the universe is probably evolving. Ideally, we'd like to have a power spectrum that measures the universe when it's static, but for this Z range and those times, it's probably not the case. Strictly, we can't use the delay spectrum method for this observation because these baseline drifts that I talked about are too long at these low frequencies and the frequency range used. So the approximation that we got by Fourier transforming these baselines to get the line of sight power is starting to break down. But for the future, once we get a better understanding of our systematics and can remove them, and we take a longer observing time to average out problems and noise, and use a shorter frequency range, which will deal with these problems up the top here, at the same time with a higher frequency resolution as we shorten the frequency range, the Z range. Or we could switch to a different method, but at the moment we're not planning to do that. So we wanted to do some noise analysis to find out if we could make a detection.
You have 5 more minutes.
Okay. So what the method that we've used for that power spectrum is basically incoherent averaging of baselines. Each baseline is observed at 9-second intervals, converted to power at each interval, and then they're averaged over time. For coherent integration, we want to average all the 9-second intervals first, then convert to power, which will give us much better noise reduction. However, it's hard to get large numbers of these intervals for coherent integration because they have to line up and be observations of the same sky. But we have a method to do it. So we did some noise simulations, and this is 3,000 hours of just thermal noise using coherent integration. This is what a power spectrum looks like. And we used lots more different frequency bands. So from this, we can extract delta squared values that I'll talk about from now on. Anastasia has provided us with plots of models of the signal with delta squared on the y-axis, 1 plus z on the x-axis, and the crosses are the noise level that we can get with 3,000 hours in coherent integration. This is just a selection of theoretical models, and these are the parameters used, but I won't go into them in detail. So what we can see is that for some of these models, they go above our noise level, which means that we may be able to detect them if they're there, of course. The sensitivity allows us to detect Lyman alpha and X-ray peaks that are in this highlighted region. The Lyman alpha is from these stars as they arise, later on X-rays from X-ray binaries. So we'll be able to put constraints on the timing of these processes. The orange line is an exotic scenario that was motivated by the edges detection. There are lots more of these, but it's also going above our sensitivity levels, so we'll be able to detect some of these. So a broad range of these edges models could be studied at this level. So in conclusion, we have a wedge power spectrum with some issues, observing at Z of 28 for the 21 centimeter power spectrum. Obviously, I've skimmed over the work and left out a lot, but hopefully there'll be a paper coming. The noise analysis indicates that we could make a detection according to some models. This is our sort of first attempt to make sure that we can do it, find out what the issues are, and develop tools and do the noise analysis. So thanks for the opportunity for me to give this talk, and I'll finish there.
Thank you very much, Hugh, for that interesting contribution. So again, my applause on behalf of all of us. And I would like to open the floor for questions and comments. All right. So Hugh, maybe I could ask a question. You noted some interesting features in the wedge that you can kind of already see but not know where they come from, right? Like that outer envelope.
Yeah.
I imagine that's I mean, at what level is that relative to your 10 to the 12?
I don't have the figures off the top of my head, but this is a log plot, so they are quite low relative to the peak of the foregrounds. So the log plot, makes this all visible, but they are at a fairly low level, and we have extracted the values, but I can't equate them at the moment.
Okay, do you have any idea how far above the level that you need to finally get at those are still?
Yes, the whole power spectrum for this 4 hours of data is way above the signal level, including outside the wedge, far outside the wedge.
Oh, okay. So even far outside the wedge, you're still quite a ways.
Yeah, so this outside the wedge, we have a delta squared of about 10 to the 12, and we're looking for 10 squared.
Apologies. I wasn't aware that the 10 to the 12 was already well outside the wedge. So that, okay.
Oh, yeah.
Okay. Thank you. Other questions or comments? No. Well, then I would like to thank you again. Thank you very much. And I would like to thank all the speakers and attendees of this morning session, at least for me, morning session, possibly evening or late night session, depending on where you are in the world. And I would like to invite you all to the next session, which will start in 6 hours' time, and which will conclude the epoch of reionization and cosmic dawn day in this meeting. So thank you very much, and I hope you will join us when we reconvene later today.
And Ralph, can I interject with just a comment that there's also a coffee and tea room that is now open for people to join if they'd like to have some discussion after the talks.
Oh, great. Yes, of course. Sorry, I forgot about that. Thank you, Jason.